Hey everyone, my name is Teal. I'm a TA for your deep learning class this fall, and my responsibility is to show you different demonstrations of code to actually run deep learning models in practice. So let's go ahead and get started. I'm in a browser page where I've pasted the link to the first demo. This is the demo that we're going to go through together today. Now, I don't want you to have to write down everything that we're going through because I want you to be able to focus on what we're doing and ask questions and answer things as they come to your mind. So you're going to get access to each one of the demos that we're going to go through. If you want to run one of these demos yourself, and this little link is here, you can just open this in Collab. If it's not there, then you can copy and paste this link. Go to collab.research.google.com, which is an amazing Google offering that allows you to run code online for free as long as you have a Gmail account. And then if you want to open the particular Python notebook that you found from GitHub, you can go to GitHub, copy and paste the URL here, click return to find it, and then choose which one of the notebooks that you want. The notebook that we're going to go through today is the first one for this class, which is called the Basics. Once you open this up, you can click Run All, and this will connect to a runtime and run all of the code in this demo so that you can see what happens and what code causes what outputs to occur. Now, today, we won't actually go through this existing demo. We'll build it up from scratch, and I'll write it myself. Of course, I won't write as much of the comments and the words that are here. So if you need that as a resource, I suggest you go to the GitHub link, which will be available on the class website, and open this way in a Collab notebook for yourself. Okay, so what are we actually going to do today? We will do a new demo. I'll just delete this, clear this out. And what is this demo called? This is going to be PyTorch Basics, which will be hopefully a good introduction for you on the Python library called PyTorch, which we're going to be using in this class to run deep learning models. Now, there are two things that we're going to do. I'll call them two exercises. The first exercise, exercise 1, is to work with variables in PyTorch. These are called tensors. That's what PyTorch calls their variables. And we'll see several interesting features with them that make them uniquely suited for deep learning computation. The second exercise is that we're going to actually train and run a deep, I'll put that in quotes because it's only a single layer, a deep learning model on the task of recognizing handwritten digits. And I'll explain what I mean by that in a little bit. Before we get there, I will assume some prerequisites for these demos. Basically, I will assume that you have a working familiarity with Python and NumPy, which is a standard Python library, which is often used for mathematical analysis. Okay, if you don't have familiarity with these things, that's okay. There are plenty of amazing resources online. If you'd like my help, please reach out to me and I would be happy to point you in the direction of some excellent resources. With that out of the way, let's describe the goals that we have today. The first goal from the first exercise is that we want to understand PyTorch variables, which are called these tensors, how to create them, how to work with them. And I want you to realize that PyTorch in these tensors keep track of how variables are computed. What this means is that when we're computing something, we keep track of that implicitly in the tensor structure, and that'll be very useful when we're going to compute gradients, which is the way that we train our models using gradient descent. We'll get to that in the next few weeks, and you'll have a better understanding of why this is so useful. But today, I want you to see that it works and how you can go about using it. From the second part of this exercise, I don't expect you to understand everything that we're doing. This is the first week after all, but I just want to show you it so that you have some passing familiarity that we'll be able to build off of in the rest of this semester. In particular, I think you should, after this, have an idea for how to load training data in PyTorch. This is very useful because for all of the deep learning tasks that we're going to be doing, we need good data sets. Also, once you're working with a data set that you haven't seen before, it's very important to have some skill or some ability to investigate the data set and get an understanding of what's going on. So I'll show you how to do that today as well, and that's a general skill that will be very applicable for all of the deep learning that you do. Now, there are two more things which I don't expect you to grasp 100%, but I just want you to look at and maybe get a better understanding of what's going on. The first one is how to define a deep learning model. So I'll call that a PyTorch model. And in addition to that, how to train a model in PyTorch. There will be a lot of steps here, and we'll be repeating those steps in different forms throughout the semester. The point of today is not to understand, again, 100% of what's going on, but just to see it for the first time, because this is what we'll be doing the rest of the semester. In addition to that, I would love it if you ask questions. So please ask questions. Of course, that's difficult because this is a recording. If you're watching this as a recording, and if you watch future demos as a recording, you are more than welcome to post your comments on Brightspace or whatever discussion platform we end up using. I will also, after the first demo, so starting for the second demo and on, I'll be holding these demos in person in Rogers Hall's room 221, and I'll announce that location and when it's going to be. You are more than welcome to show up in person. I'll also be holding them on Zoom at the same time. I'll just connect to a Zoom meeting. And either way, if you're watching on Zoom or in the classroom, you will be able to ask questions live. Please ask questions live because it answers the questions that you have on your mind and because it makes the process more engaging for me. It's much more fun when I get some feedback here and I get a sense of what you're thinking and we can kind of have a more shared experience. Okay, so with all of that out of the way, let's get into some actual coding. We'll start easy. We'll import some libraries. So I'll import NumPy as NP. This is a math library, which is generally useful in Python. Math library. We'll also import Torch. This is PyTorch. And this will have a bunch of different functions that we'll be using for training. We'll also import Torch Vision. This contains the specific data set that we're going to use, the data set we're using today, and some other functions that will be helpful for us down the line. And then finally, we're going to import matplotlib.pyplot as PLT, and this will help us plot things, such as the images that we're working with. I'm going to go ahead and run this. You can click this button over here. Collab will connect to a runtime. In this case, we're just going to use a CPU right now, but we'll be switching to a GPU later on to run some of our matrix multiplications more quickly. And it worked. So we've imported these libraries, no errors so far. So the first thing that we're going to do is investigate the relationship. Maybe I'll put this up here or here. Exercise 1, relationship between the NumPy library, which I hope you're all familiar with, and PyTorch in the context of some variables. So let's start off, and we're going to make a variable, call it A, which is a random 2x2 matrix. Random 2x2 matrix in NumPy. So I can run this and I can print out A, and sure enough, this is a 2x2 matrix, and these entries look random to me. If I run it again and again and again, the entries still look random. From this, I'm going to create another variable, which will be a torch tensor. And the way I'll construct this particular torch tensor is importing it or loading it from NumPy. So there's a handy NumPy function, which converts the matrix to a tensor. Now, this tensor is what we'll get used to in PyTorch. Now, I want to actually look at these things. So I'll print A, and then I'll print B. When I do that, I see that this is the 2x2 matrix in NumPy, and this is the same 2x2 matrix in PyTorch. So the data hasn't changed, but what's different is that I can tell it's a tensor because it's called a tensor, and it also keeps track of the data type of this tensor. Of course, in NumPy, you also store the data type, but it's not as immediately obvious. So far, these two objects look exactly the same. Let's see how they're different. The main intuition here is that in PyTorch, you are storing basically any data you have as a tensor. A tensor can be a nice generalization of a matrix in that it just doesn't have to be two-dimensional. It can be three or more dimensional, and that'll be useful for us when we're passing around not just matrices, but batches of matrices, as we'll actually do towards the end of this demo. The other thing that's very useful about tensors is that we can keep track of the computational history, which is how we computed something in PyTorch. That'll be very helpful for us when we want to do back propagation or gradient descent. So first, let's try doing some computations on A, where A is our NumPy matrix. So I'll define new A. New A is equal to A plus 10. And I'll print out new A. This should just be the same matrix that we had before, but I'm adding 10 to each one of the entries. Sure enough, it's the same thing, but I've just added 10. After this, I'm going to do something else. I'm going to square each one of the entries by going like that. And then if I print out new A again, I'll get now this value squared. I don't actually know what 10.54 squared is, but it's a little more than 100, and this is a little more than 100, so I believe it. In addition to that, finally, I will take the sum of all the entries in this matrix, which aren't too many. When I print it out, I should get a single number, which should be pretty large, probably the sum of all of these things. Now, I've done these computations and I get some output, but it's not clear, given this output, how these values, which we're going to think of as weights when we're actually running a deep learning model, how these weights influence this output. And for that, we're going to turn to PyTorch and tensors, because tensors keep track of the computational history. And this is what happened previously. So let's show that with an example with the same stuff that the same code or the same operations that we just did. I'm going to create a new variable, new b, which will be b, which remember is just the tensor version of the matrix A. But now I'm going to set this requires grad flag. This requires grad means that we'll keep track of the computational history. And I'll do the same things that I did before. So new b is equal to new b plus 10. I'll print out new b. And now we see the same values that we have up here, except one more thing, which is actually going to be very useful. It's going to tell me the last operation that I did to get here. And that's that I did some addition. And the particular way I did this addition is calling add backward 0. That's not so important for us right now, but what is important is that it's keeping track of how we got here. So it knows that we added 10 to get here. Then I'll repeat this. The next operation was that we squared each one of the entries, and I'll print new b again. And then the last operation is that we took the sum of all of these. And I'll print that out. Oh, yep, there we go. Okay, now if you compare these, all of these numbers are exactly the same, except what's different is that I keep track in the tensor of the last operation that we did. So to get to this point, when we printed out this matrix, the last thing that we did was we multiplied it by a power, which is what this function means. When we got to this single scalar, the last thing we did is that we summed it up, which is what this is telling us. Now, this was very useful because it allows us to take derivatives very efficiently. Let's see an example of how we go about actually taking one of those derivatives. But before we do that, instead of working with these matrices, let's work with scalars again to get some intuition for them. So we're going to let x be a real number, y be another real number. So let x and y be random real numbers. And we're going to define z equal to x squared y. Now, we know from calculus that dz dy, the derivative of z with respect, or let's do dz dx, the derivative of z with respect to x is equal to what? That should be y is a constant here, and then we're taking the derivative of x squared by doing the chain rule. We knew that's 2x times the derivative of x with respect to x, which is 1. So we know analytically that the derivative of dz d, or that the derivative dz dx is equal to y times 2x. The question that we're going to ask is, can we get the same answer using tensors? Let's see. The first thing that we're going to do is define some random variables. I'm going to define x equal to a random scalar. So I'll initialize a random 1x1 matrix. 1x1 matrix is simply just a number. I'm going to define I'm going to call that y. I'm going to call this x. It's also going to be a 1x1 matrix, except I'm going to set the requires grad flag equal to true. This will enable us to keep track of the gradient with respect to x. That's helpful because we want to compute dz dx. That's the derivative of z with respect to x. That's the thing that we want to keep track of. And then I'm going to define z. We said z is equal to x squared times y. For context, let's print out what x is. Let's print out what y is, and let's print out what z is. If I run this, then I'll get some tensors. If you do the computation, if you square this and multiply by this, then you should get 0.207. I'm not going to do this because I trust the computational and calculator abilities of Python, but you're welcome to. Now, to do the thing that we're interested in, which is computing the gradient of z, or the derivative of z with respect to x, we're going to call z dot backward. This computes the gradient of z with respect to its descendants. Descendants here are everything that we use to compute z. So x is a descendant of z and y is a descendant of z. Now, this is the answer that PyTorch will have to dz dx. That is going to be x dot grad. X dot grad is the gradient of z with respect to x. We specified that we want to keep track of that by saying requires grad equals true when we defined x, and that we want the derivative of z, and we know that's the case because we called z dot backward. So let's compare its answer there with what we know analytically. The thing we know analytically, which we just showed right up here, is that the actual derivative of this is y times 2 times x. And with any luck, these two numbers are exactly the same. So we were able to compute the gradient of z with respect to x using torch variables under the hood simply by calling z dot backward. Now, in this case, you might say, oh, why would we need to use tensors? Because this was such a very simple operation. We analytically knew exactly what this value was. But in general, when we have very deep models with lots of layers and lots of non-linearities, we don't know exactly what the gradient is. And that's why it's very useful to use PyTorch and tensors, because it automatically keeps track of all of that information for us. Now, of course, we're doing this with single scalar values. Those are real numbers. The thing that we actually care about doing this with respect to are large matrices. So we're working with a lot of data. We'll represent that in large matrices, and we want to compute the gradients with respect to each one of the weights that we have in the model. So that's to say, we'll be doing this in higher dimensions. We won't go that big, but let's try like a little bit bigger. So we'll try the same thing in a slightly larger dimension. I'm lazy, so I'm just going to copy and paste this code, and then we'll modify it slightly. So let's define y to be a 2x1 vector. And because it's no longer one-dimensional, I'll call it capital Y and capital X. Then I'll compute, this should be a 2x2 random matrix. And then for the dimensional analysis to make sense, I can say, sure, I'm going to square x, so that'll still be a 2x2 matrix, and then I'll multiply by y. That's fine because it's a 2x2 matrix times a by 2x1 vector, which in terms of your linear algebra, that works out, that's fine. And then the thing that we're going to do is compute z as the sum of these things. And then we're going to print out x, we'll print out y, and we'll print out z. Now we'll do the same thing, we'll compute the gradient of z with respect to its descendants, and then we'll call x here, and then we'll see if the derivative that we actually compute is the same one that we know, which is analytically true. So if we run this code, now we get, as we wanted, x is a 2 by 2 matrix, y is a 2 by 1 vector, z is a single scalar because it's the sum, and we get a tensor of each one of the value of z with respect to each one of the values of x, and we see that this matrix is the exact same thing as this matrix. So yet again, we've used PyTorch to show the thing that we know is analytically true, which in this case is computing an easy derivative. So the benefit of this is it doesn't just work in one dimension. As we saw in the previous example, it works in higher dimensions. And this is what's going to be going on under the hood every time we end up training a model. We'll just be calling a series of backward functions on it. And whenever we compute backward, we get the gradient with respect to, in our case, the function we care about, which is the loss, the measure of how good our model is. And then when we run back propagation or gradient descent, we'll be updating that value so that we'll improve our model over time. If that didn't make sense to you, that's okay. That's the whole point of this course, and you'll get a better understanding of this in the next few lectures and the next few demos. But the thing I want you to take away from what we've gone through so far is that the things that PyTorch uses are tensors, and tensors are useful because they allow us to keep track of computational history and very easily compute derivatives. Excellent. So the next exercise that we're going to do is actually training a deep, or I won't call it deep, I'll go training a model. Excellent. So let's jump in here. Again, I want to remind you that if you haven't seen this stuff before, it's kind of difficult. And for it to work, we need to do a lot of different things. And there isn't really a great way to just do a few of those things at a time. So I'm going to show you all of them at once. And I just want you to sit back, relax, and try to understand as much of this as you can. If you don't understand all of it, that's to be expected. I just want to see you to see it now. And hopefully by seeing it at least once, you'll get a better sense of what's going on in the lectures and the demos going forward. So the exercise is training a model. Before we do that, the first step is to get some data. I'm going to copy and paste the code to get this data because it's kind of gross and I don't want to type it out. This, you don't really need to understand what's going on here, except that we're loading data that we're going to use for training and for testing. Notice that this is from Jan LeCun, who's a prolific computer scientist over at NYU Current. So one of his big things was packaging this data set for everyone to use, which enables us to do things like this, which is very easily train models on this wonderful data set. Okay, so let's take a look at what's going on here. We'll do our best to investigate this data set, which is called MNIST. So the first thing that we can do is take a look at training data. In particular, let's take a look at the length of training data. If we look at it, there are 60,000 things in here. That's a lot of things. If we do the same thing for test data, I'll make a new code block. Length of test data, this is 10,000. So this tells us there are 60,000 examples of training data and 10,000 examples of test data. That's a lot of data, which is excellent because we need lots of data to get deep learning models to work. Let's take a look at just one of them. So if I call training data 0, that indexes into the first one, I get a bunch of matrices and numbers that don't really make sense to me right now. But I do know that this consists of an image and a label. And if I unpack this value like this, and then I take a look at image.shape, so let's print image.shape. This is just image as a tensor, and then shape is the dimensions of that tensor. And then I'll also print out label. If I print out image.shape, I see that this is a tensor with dimensions 1 by 28 by 28, and the label is just the number 5. So this, I'll write this in a comment, is a 1 by 28 by 28 image. What could this mean? Well, the 1 means that there's only one color in this image, one type of pixel value. And then 28 by 28 means it's a grid of 28 by 28 pixels. The label is a single number which corresponds to what is inside that image. Let's take a look at that image to see what's going on. So I'll use the matplotlib imshow function, which is just a way of showing an image. And if I call that on this, I'll get an error. That's because a 1 by 28 by 28 is not a valid shape. I'll just squeeze this. Squeezing it turns it into a 28 by 28 image, which just removes the singleton 1 there. Once I do this and I run it, then I'll see an image. And if you squint at this, this maybe does look like a 5. So we figured out that inside this training data, there are lots of images, 60,000 images. All of these images, we assume, generally all of the training data is uniform, are 28 by 28 pixels of one type of color, and it encodes a digit that was handwritten by someone. And the label corresponds to what that digit is. So here, this digit is a 5. Excellent. So we've taken a look inside this data set. The next thing that we're going to need to do is there's a lot of images, so we don't want to use all of them at once. We're going to use a data loader, which is this handy function inside Torch for loading batches of data. We do things in batches because we can't actually run computations on 60,000 images at once due to space constraints. Maybe actually we could because our hardware has been getting much better, but there are lots of examples where we still need to do batches when the data gets more interesting. Okay, so again, I'm going to copy and paste this. It's not so important that you understand exactly what's going on, except that I'm just wrapping the training data inside and the test data inside this thing called a data loader. Now let's take a look at what this does. This is something that we can turn into an iterable. So I'll say iter of train data loader. I'll get the next one of the things here, and then I'll unpack that into images and labels because I know that that's what's inside it. Generally, if you want to understand something in PyTorch, it's very good to always print its shape. So I'm going to print images.shape and I'm going to print labels.shape. When I do this, I see that images is a 64 by 1 by 28 by 28 tensor, and labels is a 64 length tensor. This makes sense. I have 64 images, such as this one that I saw previously, and I have 64 labels corresponding to the number that's inside these images. So we loaded a batch. Each batch has 64 images in it. Let's say we wanted to load a batch of 128 or some other number. It doesn't even have to be a power of 2. How would you accomplish that by modifying the code above? You can pause and think about that for a second. And the answer is that we can just change this parameter here. So if I wanted to change the batch size to be 128, like this, then I can run it again. And now I have 128 images and 128 labels. I like 64, it's a beautiful power. So I'll just keep it. But as our computers get more powerful, it's less important that we use small batches. Okay, excellent. So now that we figured out how to train or how to load data, load our training data, the next thing that we're going to use is we're going to define our model, our loss function, and our optimizer for training. Now this is going to be part of our 3-step recipe for machine learning. And I think this is a very powerful framework for viewing a lot of what goes on in deep learning. As long as you understand that there's a model, a loss function, and an optimizer, and you ask questions about what each one of them are, then you can basically understand almost everything that's going on in deep learning. So I challenge you, go to a conference, a high-powered one where people are presenting all their fancy models. You walk in and watch someone's talk. And after their talk, if you understand what their model is, what their loss function is, what their optimizer is, you have an understanding of basically the entire research that they've done. So most research in deep learning works with either changing the model or changing the type of loss function. And this is a very powerful framework that will take you all the way from the beginning in this class up to research level understanding of what's going on. Okay, so enough of me rhapsodizing about it. Let's go ahead and write some code here. The first thing that we're going to do is define our model. We're going to do that using the Python class framework. And whenever we define a model in this class, it'll look, or in this class, the class being this semester, it'll be similar to what we're about to do. There's always an initialization function, and this gets run whenever we initialize one of our models. We need to call this for some reason that I still don't understand, but it doesn't work if I don't run it. So I put it there. And we'll define some variables that we'll use in our model. In our case, we only need to define a single layer. We're going to call that layer linear. And this is going to be a linear layer from the PyTorch library. The input dimension here will be 28 by 28, and the output dimension will be 10. Again, this is a great place to pause and check your understanding. Why is this the size of the input, and why is this the size of the output? Now that you've gotten a second to ponder, let's think through this. The thing that we're going to pass into our model is one of the images. What's the dimension of this image? The dimension is going to be 28 by 28 because that's the number of pixels that we have. So this is the input size because that's the size of our input image. Why is this the size of our output? Well, I actually haven't told you this yet, but, or maybe you know, there are 10 digits that we're going to be using in our MNIST data set, and those are the numbers 0 through 9. So there are 10 possible labels for each one of our images. So we're going to have an output corresponding to each one of those values in our model. And that's it. That's the only thing that we need to do at the initialization step. The other thing that we need to define for our model is a forward step. At the forward step, we pass in some input x. So this runs when we call the model on image x. The first thing that we're going to do is change the dimension of x. It is, as you saw, a 28 by 28 tensor. We're going to change that so that it's a 28 times 28 is 784. It's a 784 length vector. That's because that's the input size to our linear layer. And then we're going to call our linear layer on it. We're going to say x equals self.linear of x, and then we're going to return x. And that's it. That's the extent of the model that we defined. I think that after seeing this for the first time, you'll have some questions about that, and that's great. Please feel free to ask at office hours or online. We'll be getting a lot of familiarity with this, so we'll also get a lot of other chances for you to understand what's going on here. Now that we've defined this, we'll go through our three-step recipe. The first step of our recipe is to define our model. Our model is going to be a call of this class. So model equals call of this class model. There aren't any arguments that I passed in besides itself. So I just call this. And I have our architecture, which is our model in this case. The second step is going to be to define our loss function. Our loss function here is going to be cross entropy. I won't tell you what that is quite yet, but once in the lecture, you'll get a better understanding of it. All you need to know is that this will enable us to tell us how different the predictions are made from our model from the true labels. And then our goal is to reduce the difference between the predictions and the labels, and we do that by using gradient descent. Now, the third step is the actual way that we use gradient descent, which will be our optimizer. Generally, this is some variant of gradient descent. Here, this is called stochastic gradient descent, or SGD. The things that we'll be optimizing over are the parameters of the model. The parameters of the model are defined in this linear class. And we'll also define the learning rate. The learning rate will be fairly large because our model is quite small here. So with these three things in hand, we have our three-step recipe. We have our model, our loss function, and our optimizer. Now we'll be ready to, we're ready to do some training. Actually, before we do that, there's one more thing. No, I'm not sure if we need to do that actually. Let's see if we can just go ahead and do some training. Great. So now we're ready to do some training. We're going to keep track of our training loss and our test loss as we go so that we can visualize how they change over time. So I'll initialize an array, which is train losses, and then another array, which is test losses. And then I will train for some number of epochs. Because this is an easy task, we only need 5 epochs to be able to learn it fairly well. And in each epoch, we're going to do several things. We'll initialize our training loss and our test loss for that epoch to 0. And we'll do 2 passes through our data. The first will be an evaluation process. In the evaluation process, we go through our test data. We look at all of the test data, and then we see how well it performs, or how well it's doing on how well our model is able to do on the test data. So to do that, we will just say for I data in enumerate test data loader. Actually, we don't even need to do enumerate here because we're not using I. So we can just say for data in test data loader. Remember, each one of these batches consists of images and labels. So I'll say images and labels is equal to data. Then we're going to get some predicted output, and our predicted output is going to be equal to our model called on our images. So we're calling our model on 64 images at once, and this is where a tensor is very nice because it handles all of that under the hood, and we don't need to use a for loop or anything else. Everything is run in parallel in a very efficient way. Once we have our predicted output, we'll define what's called our fit, and our fit is the loss function, or really the difference between what we predicted in the predicted output and our labels. Once we've done this, we'll add this to our test loss. And normally, as you remember, fit keeps track of a bunch of information in a tensor, but we just want that scalar value. So by calling item on it, I extract just that value. Maybe I'll add some comments here. So in this line, we're unpacking our data. Here we're calling our model on images. Here we're comparing our predictions to the true labels. And here we're saving our fit, or how well we did. So this is the evaluation process, and we haven't actually done any training yet. So if I just ran this code right now, maybe I can do that. Well, I'll also need to print out what our test loss is. So maybe I'll save that as, I'll just print it out. So if we print out test loss, and I'll divide by the number of things that we have in our data set, so that's dividing by len training data, you'll see that this is the exact same value every time. That's because no training is going on. We're not doing anything to update our model. So an evaluation process isn't enough. We also need to do a training process. The thing I want to impress upon you is that the training process and the evaluation process are mostly similar, except for a few key differences. So all I did right there is just copy the code for the evaluation process down here. The main difference is that we're using, or one of the differences is that we're using a different set of training data from the testing data that we do. And the purpose of that is so that if we overfit our model to the training data, we want to be able to tell that we've overfit by looking at its performance on data that hasn't been trained on. Okay, so the first thing that we do here is we extract the images and labels like we did previously. There's one step where we zero out the gradient in our optimizer. This zeroes out the gradient values. And the purpose of this is so that we get a fresh gradient every time we do gradient descent, which is important. It's important that we don't like keep track of the same thing over time. So that's why we're printing it out here. Once we zero out the gradient, we'll do the same thing where we do a prediction. And we're going to compute our fit. Then we're going to call backward fit.backward, and this computes the gradient of the fit with respect to all of our parameters in the model. Compute the gradient of the fit with respect to the model parameters. And then finally, this is the actual learning phase, or the learning part. We're going to do optimizer.step. This updates the weights of the model using the gradients that we just computed. And finally, we're going to update this to the training loss. So the first thing I want you to realize is that these two blocks of code are mostly similar, except for some differences. There is this line, there's this line, and there's this line. And these three lines together makes the difference because this allows us to zero out the gradient, we compute the gradient, and then we update our model using that gradient. Again, if this doesn't make sense to you, that's okay. We'll go over it in more detail in the lectures and in future demos. I just want you to see it once. So as we go, let's keep track of our training and our test loss. So I'm just going to copy some code here. This divides by the number of batches that we have, so it's a loss per batch. And then we're also going to print out this, which will print out the current loss at this epoch. So let's run this code, and hopefully we'll see some learning happen. Sure enough, the loss that we saw for the training data and the test at the beginning has decreased as we keep going. So it started off at 920, and then it's at 517, and 405, etc. So this is really good. It looks like our model is doing some learning. It turns out that I think we'll only need 5 epochs to learn this task well. And before we do anything else, let's use the train losses and the test losses that we kept track of to plot the losses as a function of iteration or a number of epochs. For epochs, these are our training steps. And when I run this, I'll get a nice pretty graphic where I have the test error up here and the train error down here. It says error, but it's really the loss. It's the fit that we just computed. Now, one question that I have for you is why does it look like the training error is always less than the test error? Maybe something weird is going on here, but in general, the test loss is larger than the training loss. And I'll give you a few moments to ponder that, and then we can answer it together. Well, the answer is that we are training our model on the training data. So it really only, the thing that it learns is the training data, and it doesn't learn anything about the test data. So we expect it to have much better performance, which means lower loss, on the training data. The test data is similar to the training data, but it's not exactly the same. So we expect some natural variation between the performance on the test data and on the training data. So in general, because of that, the training loss is lower than the testing loss. Okay, so now that we've done this and we've trained our model, we see its loss goes down, but we aren't exactly sure 100% yet at what our model is actually doing. So let's look at what our trained model does. We could define new variables, but in this last step of the training process, we already defined some images and some predicted output. So instead of redefining these things, I'll just use these that were defined up here. Again, I'm lazy. So if we look at predicted output, this is a very large tensor. Whenever you get an output like this, the best thing to do is to look at its shape. So if we look at its shape, we see that this is a 32 by 10 tensor. Here, because it's the very last batch, we don't have exactly 64 images in it. It looks like we have 32 of them. And each one of these corresponds to the 10 output dimensions that we get from our model. Now, the way that we convert from this output to classes is we take the maximum one of these values, and in particular, like whichever dimension corresponds to the maximum value, well, that's the thing that we're going to predict as our label. How do we do that in practice? Well, I'll keep this up there. Maybe I won't. I'll just write it down. We have our predicted classes, and I'll take the max of this thing with respect to the first dimension. Or sorry, dimension 1, which is really the second dimension because indexing in Python starts at 0. If I do this, this will output both the maximum value and the dimension that corresponds to the maximum value, but I only care about the dimension that corresponds to the maximum value. Now, if I go to print the predicted classes, I'll get predicted classes. This will be a long tensor. The shape of this, let's look at that really quickly, should be 32. So these are the predicted labels for 32 images. Without looking at every single one of them, I'm not actually sure if they're correct. So let's look at the labels and compare the labels to our predictions. Sure enough, this looks really good. So we predicted 9552, and the true enough, that's 9552. It looks like a lot of these disagree, but of course, not all of them. In particular, it looks like our model thought the second to last image was a 4, but in reality, it's a 2. So let's look at some of these images. I'll consider some index. I'll choose the index I equals 1, and I'll print out what the predicted value of that is. So the predicted value of this is predicted classes in the ith index, and I'll print out the true label. The true label is labels at the ith index again. And then I'll use the matplotlib function imshow to plot the ith image. Remember, I need to squeeze it, and then if I call this, I'll get, oh, actually it works, never mind. I don't need to call CPU. Oh, I did, right, because I didn't put anything on GPU. Okay, so sure enough, we're predicting, so it's in a tensor, I don't like that, so I'm just gonna write item here. When we run this, we're predicting that it's 5, the label is a 5, and it clearly looks like a 5. So this corresponds to this image. If I want to get this image, I think that'll be at index 30. If I look at index, oh, sorry. I coded this so I could do this easily. I equals 30. Sure enough, I think I understand why our model is having trouble here. If I looked at this, I would not think that it looked like a number at all. Maybe it's some kind of reptile or snake with its tail up in the air. Something, I have no idea what this is. But our model is predicting that it's a 4. I can kind of see that it's a 4, but in reality, it's a 2, which maybe I could believe because there's like a little dot in the middle, so it's like a circular pattern. But in general, I do not fault the model for getting this wrong. I think I would get it wrong as well. It looks like we also have disagreement at this one, so let's go look over there. This is 30, this is 29, 28, 27, 26. So if I change I to 26, hopefully we get something else that's interesting. Cool, so we're predicting that this is a 7, but the true label is an 8. Again, I wouldn't call this a digit. If I'm told it's an 8, I kind of see that it's an 8. I don't know that I agree that it could be a 7, but I really don't know what's going on here, so I'll give it to the model and agree that this was a very hard image to try to classify. Okay, great. So this is all I have for you today. Thank you so much for making it all the way to the end of the first demo. As I mentioned at the beginning, the rest of the demos will have a live or in-person component if you would like to show up. It's optional, but I'd love to get to meet you and interact with you, engage with you as we go through these. So please come, I'll make an announcement as to where that is. And I hope that you stay in this class and get a lot out of it. I know I got a lot out of it when I took it, and it really opened my eyes to a deeper understanding of the way deep learning works. So I'll sign off for the day, and thank you very much for your attention. If you have any questions, please feel free to post them on the online discussion platform.